Hi, myself Dr. Priyadip Das, Research Associate Professor, Department of Chemistry, SRM Institute of Science and Technology. Today, we are going to discuss the continuation of our previous lecture, that is the organic photochemistry, absorption of light by organic molecules, part 2. So today we are going to discuss about EZ isomerization of alkene. One of the most important aspects of the photochemistry of alkene is the EZ isomerization around the carbon-carbon double bond. This is also valid for cycloalkenes with the obvious expectation of the cyclopropenes which exhibit a distinct photochemical behavior, and cyclobutanes and cyclopentenes where the ring is too rigid to allow sufficient twisting of the double bond. The photochemical isomerization of E-stilbene as shown below has been applied in the preparation of phenanthrene as Z-stilbene undergo electrocyclic ring closure to the dihydrophenanthrenes, which in turn are easily oxidized to phenanthrene, and this sequence has also been employed in the synthesis of benzoquinolines or of benzoquinolidines. Here we see three different examples. This is the another important feature of this reaction of cis-trans isomerization. In this synthesis of highly strength E-cycloalkene, thus the EZ-cycloocta-1,3-diene has been obtained from the ZZ compound in sensitized irradiation, while the E-cyclooctene was obtained from the Z isomer by direct irradiation. And the synthesis of a trans doubly bridge olefin has also been reported and shown in the last example. Now, here we are going to discuss about the reaction of cyclohexene and cycloheptene. The E isomer of the cycloheptene and cyclohexene are usually not stable enough to be isolated. Nevertheless, they can be trapped by the alcohol, or as for cycloheptanone, as shown in the example, or observed stereospecifically as for phenyl cyclohexene. So this later olefin also undergoes photoaddition reaction to the alcohol, but via electron transfer from the alkene to the excited sensitizer, and the resulting radical cation then reacting with the solvent to get the final product. Here we are going to discuss about the cis-trans isomerization of alkene by direct irradiation. So in this mechanism by which the cis-trans isomerization occur in terms of the sample model involve the excitation of an electron to a planar excited state which subsequently relaxes to the twisted state. A simple representation is given in this figure. A small activation energy of 2 kilocalorie per mole is required to twist the planar trans singlet to the twisted singlet state, and decay from this twisted state can give either cis or this trans stilbene as shown in the figure. However, as mentioned earlier, the trans form absorb more light at the exciting wavelength. Here we can see the lambda max trans equal to 16,300. Then does the cis form where the epsilon max value is only 2,880, and consequently the trans isomer getting converted almost completely into cis isomer. So the synthetic utility value of this trans-cis isomerization lies in the fact that more stable the alkene can be readily converted into the less stable alkene. Some example of the result of the direct irradiation of alkene are shown below, where we can already see example where the trans isomer get converted into the corresponding cis isomer. Now this is the sensitized cis-trans isomerization. So sensitized cis-trans isomerization of an alkene can be brought about the use of triplet sensitizers such as ketone. And the sensitized isomerization of stilbene is a typical example. the composition of the photostationary state of the sensitized isomerization varies with the energy of the sensitizer employed. So in this process, if the donor species fulfill the condition of the effective sensitization and the triplet energy is greater than that of either of the geometrical isomer, then triplet energy transfer to both cis and trans isomer of the isomerization takes place. And initially from cis and trans triplet excited species undergo distortion to a common phenomena. Which is this phenomena? Triplet, which on collapsing to the ground state S0 affords a maximum of isomer. Because the sensitizer can excitize both isomer, and the proportion of cis trans isomer in the photostationary state from a sensitized reaction is lower than that obtained from direct irradiation. This is in contrast to the sensitized isomerization. So sensitizers of higher energy give photostationary state with approximately the same composition of isomer, that is 55% cis as we assume, while the direct photolysis result in a higher proportion of cis isomer, that is 93% in case of steel beam. The composition of the photostationary states depend very much on the triplet energy sensitizer. With sensitizer having triplet energy above 60 kilocalorie per mole, cis trans ratio is slightly more than 1, but a range of sensitizer having triplet energy of 52 to 58 kilocalorie per mole offered much higher cis trans ratio in the photostationary state. The higher the cis trans ratio in region result from the fact that energy required for the excitation of a trans isomer is less than for the excitation of cis isomer. The sensitizer having triplet energy in the range of 52 to 58 kilocalorie per mole selectively excites the trans isomer, since the rate of trans to cis conversion is increased, and the composition of the photostationary state is this enriched with the cis having more cis isomer. Sometimes the photochemical cis trans isomerization may also take place in the presence of halogens, as seen in the example where X equal to consider the halogen radical, and it appears that under this condition there is a photochemical product of halogen atom which adds to the alkene yielding a radical. Elimination of the halogen from the radical yields a constant ratio of cis and trans isomerization. Now we are going to discuss about the dipymethane rearrangement reaction. Dipymethane rearrangement is a photochemical reaction that converts 1,4-diene compounds into vinyl cyclopropane by a light-induced rearrangement of the dipymethane chromophore. So leading to a significant restructuring of the carbon skeleton and providing access to the structurally complex and strain-rich molecule that is valuable in synthetic organic chemistry. Here we see the two examples where the most remarkable photochemical reaction of the non-conjugated diene is the dipymethane rearrangement. And this rearrangement given by the diene having pi system separated by at least one carbon atom which is sp3 hybridized. Both the cases we have seen that says 3 is the sp3 hybridized carbon atom. As for example, we are giving here 1,4-pentadienes, and the rearrangement is also given by the 3-phenyl alkene system, the second example, okay, and in which one of the double bond is replaced by the benzene ring, and the dipymethane rearrangement is also known as Zimmermann rearrangement reaction or Zimmermann dipymethane rearrangement. The irradiation of the substrate induced rearrangement to a vinyl cyclopropane or phenyl cyclopropane derivative. This vinyl cyclopropane and phenyl cyclopropane is the final product. Now, this rearrangement is found in both cyclic and acyclic diene, and the rearrangement of the monocyclic and acyclic dienes occurs solely from a singlet state. So the sensitizing reaction of the substrate leads cis trans isomerization or 2+2 cycloaddition reaction. So the experimental result shows that the dipymethane rearrangement is a concerted process obey the Wood and Hofmann rules. Retain their configuration on atom 1 and 5, a result of actually a disrotatory ring closure between the C3 and C5. and inverts it on atom 3, the conrotatory mode. So in actual practice, the reaction is represented as one involving a 1,4 and 1,3 diradical intermediates in case of 1,4 pentadiene, since it is easier to follow the various steps necessary for the rearrangement. Now we have seen that the dipymethane rearrangement involves a rearrangement of a pentadiene skeleton with no alkyl or aryl group migration. Nevertheless, the reaction path that would involve more stable diradical is always followed. Here we can see that is the 2 diradical formation, and the more stable diradical pathway is follows to get the final product. Now we can see the example where we have seen that this way these 2 double bond break by the in presence of H nu to produce the 1,4 diradical, and then this 1,4 diradical going for a break according to the route A, where this more stable 1,3 diradical is produced, because here the radical associated with the radical on the carbon atom associated with the 2 phenyl ring, and this is the more stable 1,3 diradical, and this is the final product where the cyclopropane ring is phenyl substituted, and this is the sole product. Now look into consider into the route B, where we can see the bond breaking between the C3 and C4 carbon atom produces this diradical, and finally this is the less stable 1,3 diradical, because the radical center attached with the 1 ethyl group and 1 methyl group, and when it get the product with the cyclopropane derivative, which is substituted by the ethyl and methyl group, that is not observed, and this is the not means no, this product will not form actually. So the formation of only one product 1 shows that there is retention of configuration at carbon 1. Thus the cis-trans isomerization of bond C1-C2 must be slow by comparison with the formation of cyclopropane derivative. Similarly, formation of product 1 but not the product 2 shows the less stable radical participate in the 3-membered ring opening, which gives more stable 1,3 diradical. Reaction competing with the cis-trans isomerization at increased concentration of the alkenes are photocycloaddition reaction. An alkene in its excited singlet or excited triplet state react with either the same molecule, that is called the photodimerization, or a different, that is called photocycloaddition. In the ground state, it is react to produce a cyclobutene derivative. It's formed by the alkene, as shown in the several examples. Although the dimerization of the simple alkenes whose lambda max is equal to or less than 200 nanometer is technically difficult. So increase the alkyl substitution of ethene cause a bathochromic shift of the absorption band toward the longer wavelength. That is, the energy is reduced. So the direct irradiation where the lambda absorbance value is 224 nanometer of a neat of 2,3-dimethyl 2-butene gives the corresponding dimers. Here we can see the cis-butene give 57% all cis isomer and 43% cis anti-cis dimer, and trans-2-butene gives cis anti-cis dimer 39% and trans anti-trans dimer 60%. The dimerization reaction is actually stereospecific, and this is demonstrated by the irradiation of the cis-2-butene, which yields all cis isomer and the cis anti-dimer, while the trans-2-butene afford the cis anti-cis dimer and the trans anti-trans dimer both, as you see in the example. Now the cyclohexane also dimerize, yielding a mixture of dimeric product, while the norboran afford the dimer of A and B in the ratio of 1:10. We can see the scheme 2, then we have an idea, and this photosensitized dimerization, that is the triplet stage dimerization, occur easily with the cycloalkene, particularly the small ring alkene, because they cannot undergo cis-trans isomerization. Now the dimerization appears to favor the formation of cis-trans arrangement of rings in the dimer. Example of dimerization of cyclopropene, cyclobutene, cyclopentene and cyclohexene have been reported. And the dimerization of alkene and cycloalkene is the best sensitized by aliphatic ketone. Oxytone are formed in this reaction from the aromatic ketone. As for example, the first example, the 2-cyclopentene ring produce this molecule, and here the norborane can also be made to dimerize on sensitization, and that is preferred for the formation of exotrans endoisomer. Now we are going to discuss about the intramolecular dimerization. So the photochemistry of non-conjugated diene with isolated double bond resembles with simple alkene. So such type of alkenes give the intramolecular 2+2 cycloaddition reaction to give the bicyclic product that we see in the last example. Now the product of the sensitized intermolecular cycloaddition depends on the number of CH2 group between the two double bond. So if the number of intervening group is odd, that is n equal to odd, as for example 1,4-pentadiene or 1,6-heptadiene, the major product result from a normal 2+2 cycloaddition as shown in this first example, where n equal to 135 is the odd number and we can get normal 2+2 adduct. But if the number n is even, suppose X for example 1,5-hexadiene, the major product is formed by a crossed, that is the X 2+2 cycloaddition to form a crossed bond, cross sigma bond. You can see that is the cross 2+2 adduct is produced when n equal to odd 2, 4, 6. Now this feature is even more important in cyclic diene system where n equal to m equal to 2. That is the example of 1,5-cyclooctadiene in which X 2+2 cross 2+2 cycloadduct is the only product. This is the biradical and we are getting the cross product. But if n equal to 1 and m equal to 3 or vice versa, that is the 1,4-cyclooctadiene, the normal 2+2 cycloadduct is produced. The photoreaction of 1,5-hexadiene from the triplet state follows the rule of 5, which states that if the triplet cyclization can lead to rings of different size, the one formed by the 1,5 addition is preferred kinetically. If there is several possibilities for 1,5 addition leading to different biradical, the most stable one is formed here, and that is the simple addition, not the cross product. Now here we can see some classic example where this molecule can behave as a 1,6-diene, and in presence of light and acetone it get converted into this biradical, which in produces sigma bond, and this is considered as a minor product. And when this diene can behave as a 1,5-diene in presence of this light and acetone, the same condition, it is produce this biradical, which produce this bicyclic product according to the rule 5, and this is considered as a major product. And here we see there is a problem, and we ask this problem to complete the following cycloaddition reaction. Now the exact energy of the S1 state are not known, but the cis-oid S1 probably lies between the trans-oid S1. So there is a large energy gap between the singlet excited state and the triplet excited state, that is between the S1 and T1. Also the intersystem crossing does not take place in this case. Therefore, the energy gap between the S1 and T1 accounts for the fact that intersystem crossing does not occur in this case. And therefore, the direct irradiation of the 1,3-butadiene in solution thus give rise to the chemistry only from the singlet excited state. And here we can see the energy of the excited state of the butadiene as shown in figure, where we can see this is the gap of T1 and S0 is 59.6 kilocalorie per mole, and between the S0 and T0 in case of cis-oid system is 53.3 kilocalorie per mole. So in this example we have seen the irradiation of butadiene in cyclohexane, which produces cyclobutene from an electrocyclic reaction of the S-cis isomer, and the bicyclo-110-butane and the product of an intramolecular cross 2+2 cycloaddition of the S-trans isomer in a ratio of 6:1, where we can get this product, that is the non-conjugated process, produce this biradical and finally get this bicyclo compound, and where for the cis isomer we are getting the energetically ring closure reaction which is converted to the final product into cyclobutene. Now this is the bicyclobutane formation is particularly important in this system that contain the rigid S-trans and diene geometry, where we can, in presence of light, cross 2+2 cycloaddition reaction is going to happen, and these two radical is getting a combination and get the final product. However, the cross 2+2 cycloaddition is also occurs with the cis fused diene system, particularly in the case of cyclopentadiene. You see here also in the case of cyclopentadiene we are getting the cross product, and here we give some problem. So the problem shows that this is a diene system and which one irradiated by light in the cyclohexane system, and the solution, the compound, this is basically as a S-trans compound, and the S-trans dienes, hence cyclobutane formation will takes place via the cross 2+2 cycloaddition reaction. So here we can see that is the molecule has a rotation and it produces the converted into that S-cis conformation, and then it will go for the 2+2 cycloaddition reaction.